What is time? That's a tough question, isn't it? We all feel like we know what time is because we experience it every single day. Tick-tock, tick-tock. But here's the remarkable thing that Einstein figured out. Time is not the same for everybody. Time is not this absolute thing that marches forward at the same rate everywhere in the universe. That's what Newton thought. And it seems obvious, doesn't it? But it's wrong. Let me tell you a story. Imagine you have a clock. Not a fancy clock, just the simplest clock you can think of. It's got two mirrors, one at the top, one at the bottom, and a single photon of light bouncing up and down between them. Every time the photon hits the bottom mirror, that's one tick. Every time it hits the top mirror, that's one tock. Simple, right? Now, if this clock is sitting right here in front of you, not moving, you watch the photon go straight up, bounce, come straight down, bounce. The time between ticks is just the distance between the mirrors divided by the speed of light. Let's call that distance L. So the time for one complete tick-tock is 2L divided by c, where c is the speed of light. Nothing fancy so far. But now here's where it gets interesting. Suppose I take that clock and I put it on a spaceship, and that spaceship starts moving, not just puttering along, but really moving at a significant fraction of the speed of light. Now you're standing still watching this spaceship zoom past you with this clock on board. From your perspective, what does the light do? Well, the spaceship is moving, so by the time the light goes up to the top mirror, the whole spaceship has moved sideways a bit. The light doesn't just go straight up anymore. It goes up and sideways. Then when it comes back down, the spaceship has moved even more, so it goes down and sideways. The light traces out a zigzag path. Now here's the crucial thing. The speed of light is always the same. Always. This is the most important experimental fact in all of physics. No matter how fast you're going, no matter how fast the source is going, light always travels at exactly the same speed, about 300,000 kilometers per second. Not 300,001, not 299,099, exactly the same. So if the light has to travel this longer zigzag path and it's going at the same speed as before, it must take longer to complete one tick-tock cycle. It has to. The path is longer, the speed is the same, so the time must be longer. This is geometry. This is just the Pythagorean theorem. You can work it out with high school math. What does this mean? It means the clock on the spaceship is ticking slower than the clock sitting here with you. But wait a minute, it's not a broken clock. It's the same clock. And here's the really wild part. Everything on that spaceship runs slow, not just this light clock. Every clock, mechanical clocks, digital clocks, atomic clocks, your heartbeat, your thoughts, chemical reactions, everything. Time itself is passing more slowly on that spaceship. Now you might say, wait, Feynman, that's crazy. Surely the person on the spaceship would notice their time running slowly. But no. See, that's the beautiful part. From the spaceship's point of view, they're not moving at all. They're just sitting there. You're the one who's moving past them. So from their perspective, their clock is ticking normally, and your clock is running slow. And they're right. Both of you are right. That's what's so strange about it. There's no contradiction here because you can't directly compare your clocks unless you bring them back together. And when you work out what happens when they come back together, accounting for the acceleration and deceleration, you find that the moving clock really has measured less time. The traveling twin really is younger. This isn't philosophy. This isn't just words. We've measured this with atomic clocks on airplanes. We see it every day with particles and accelerators that live longer than they should because they're moving so fast that time slows down for them. Let me give you the actual formula because I think equations can be beautiful when you understand what they mean. If you're moving at some velocity v and I measure a time interval of t on my stationary clock, then you, on your moving clock, will measure a time interval of t multiplied by the square root of 1 minus v squared divided by c squared. That square root factor, we call it the Lorentz factor. It shows up everywhere in relativity. Let me write it out for you. Gamma equals 1 over the square root of 1 minus v squared over c squared. That's it. That's the factor by which time slows down. Now let's look at this formula carefully. When you're moving slowly compared to light, v is much, much smaller than c. So v squared over c squared is almost 0. The square root of 1 minus almost 0 is almost 1. 1 divided by almost 1 is almost 1. So gamma is almost 1, and time runs almost normally. That's why we don't notice this in everyday life. Even a jet airplane going 1,000 kilometers per hour is only going about 1/1,000,000th the speed of light. The time dilation is absolutely tiny. But as you go faster, as v gets closer and closer to c, look what happens to that formula. The ratio v over c gets closer to 1. So v squared over c squared gets closer to 1. So 1 minus v squared over c squared gets closer to 0. You're taking the square root of something getting closer and closer to 0, which itself gets closer and closer to 0. And then you're dividing 1 by that. 1 divided by a number approaching 0 gets bigger and bigger and bigger without limit. Let me give you some numbers to make this concrete. At 10% the speed of light, pretty slow by cosmic standards, time runs about 0.5% slower. You wouldn't notice that unless you had a very precise clock. At 50% the speed of light, time runs about 15% slower. Now you'd notice. If you spent a year traveling at that speed, people back home would age about 14 months. At 90% the speed of light, time runs less than half as fast. 1 year for you, more than 2 years for them. At 99% the speed of light, time runs at about 1/7 speed. 1 year for you, 7 years for them. At 99.9% the speed of light, about 1/22nd. At 99.99% the speed of light, about 1/70th. You see where this is going? The closer you get to the speed of light, the more extreme it gets. And we've tested this. At the CERN laboratory in Europe, they've accelerated electrons to 99.99999% the speed of light. That's 11 nines. At that speed, the time dilation factor is over 200,000. A particle that normally lives for a microsecond will live for 1/5 of a second. We see this. This is real. Now here's where it gets really weird. What happens at exactly the speed of light? What happens when v equals c? Let's look at that formula again. If v equals c, then v squared over c squared equals 1. 1 minus 1 equals 0. The square root of 0 is 0. 1 divided by 0 is, well, it's not a number. It's undefined. It's infinite. What does that mean? It means time dilation becomes infinite. Time doesn't just slow down. It stops. It freezes. From the perspective of something traveling at the speed of light, no time passes at all. Think about a photon, a particle of light. It's born in the core of the sun. It bounces around for maybe 100,000 years, making its way to the surface. Then it flies through space for 8 minutes and hits your eye. From your perspective, that photon has been traveling for 8 minutes. But from the photon's perspective, no time has passed. 0. The moment it was emitted is the same moment it was absorbed. Its entire journey, from creation to destruction, happens in a single instant of its own time, and there's more. Just like time dilates, distances contract in the direction of motion by the same factor. At the speed of light, distances shrink to 0. So that photon doesn't just experience 0 time, it experiences 0 distance. From its perspective, the sun and your eye are at the same location. The entire universe in the direction it's traveling is squashed flat, no thickness at all. Now I have to be a little bit careful here because technically we can't define a reference frame for a photon. Einstein's equations don't work at exactly the speed of light. You can't do a Lorentz transformation with v equals c. The math breaks down, but we can ask what happens as we get closer and closer to the speed of light, and then we can see what it approaches. And what it approaches is 0 time and 0 distance. This is why nothing with mass can travel at the speed of light. Look at what else happens as you speed up. Your energy increases. In fact, your energy is your mass times the speed of light squared, times that same Lorentz factor. As you approach the speed of light, the Lorentz factor goes to infinity, so your energy goes to infinity. It would take infinite energy to accelerate you to the speed of light. The universe doesn't have infinite energy to give you. Only things with 0 mass, like photons, can travel at the speed of light, and they must travel at the speed of light. They can't go slower. They can't go faster. They can only go at exactly c. Let me tell you something that I find absolutely beautiful about this. The fact that time stops at the speed of light isn't just some weird quirk of the equations. It's deeply connected to the fundamental structure of the universe. Space and time aren't separate things. They're woven together into what we call spacetime. And the speed of light isn't just the speed of light. It's the conversion factor between space and time. It's the speed at which causality propagates. It's the maximum speed at which information can travel. When you move through space, you rotate your path through space-time. The faster you move through space, the slower you move through time. There's a trade-off. You're always moving through space-time at the same total rate, but you can split that motion between the space part and the time part in different ways. When you're sitting still in space, all your motion is through time. When you move through space, you trade some of that time motion for space motion. And when you're moving at the speed of light, all your motion is through space and none is through time. Here's another way to think about it. In our everyday experience, we think of space as having 3 dimensions and time as being separate. But relativity tells us that's not quite right. Time is a 4th dimension, but it's a special kind of dimension. It has a minus sign in front of it in the mathematics. When you compute the interval between 2 events in space-time, you take the square root of the time difference squared minus the space difference squared. That minus sign is crucial. Because of that minus sign, there are 3 kinds of separations between events. If the time difference is bigger, we call it time-like. You could travel between those events slower than light. If the space difference is bigger, we call it space-like. No information can connect those events. They're outside each other's light cones. And if they're exactly equal, we call it light-like or null. Only light can connect those events. At the speed of light, the space-time interval is 0. From the photon's perspective, the emission event and the absorption event are at 0 separation in space-time. They're the same event. This has some pretty profound implications. We talk about the age of the universe, right? About 13.8 billion years. But that's the age in our reference frame, moving slowly through space. For photons that have been traveling since the Big Bang, no time has passed at all. They were created and they still exist, all in the same timeless moment. In a sense, for light, the Big Bang is still happening. The entire history of the universe, from beginning to end, is compressed into a single instant. Now, you might ask, if time stops for photons, how can they have a frequency? How can red light be different from blue light? That's a very good question. The answer is that frequency isn't something the photon experiences. It's something we experience when we observe the photon. The frequency depends on our reference frame. If we're moving toward the source, we see a higher frequency, blue shifted. If we're moving away, we see a lower frequency, red shifted. The photon doesn't have a frequency in its own frame because it doesn't have its own frame. Let me give you one more example to show how strange this is. Cosmic rays are particles that come from space, and some of them are particles called muons. Muons are unstable. On average, a muon lives for about 2 microseconds before it decays, 2 millionths of a second, then it's gone. Now, these cosmic ray muons are created high up in the atmosphere, maybe 10 kilometers up, and they're traveling very close to the speed of light, say 99.8% of c. Even at that incredible speed, it should take them about 33 microseconds to reach the ground. But they only live for 2 microseconds, so they should all decay before they get here. But they don't. We detect lots of them at the ground. Why? Time dilation. At 99.8% the speed of light, the time dilation factor is about 16. So while 33 microseconds pass for us, only about 2 microseconds pass for the muon. From the muon's perspective, it lives its normal lifetime and just makes it to the ground. From our perspective, it lives 16 times longer than normal and makes it to the ground. Same result, different descriptions. Or you could look at it from the muon's point of view using length contraction. From the muon's perspective, it's not moving. The Earth is moving toward it. And because the Earth is moving at 99.8% of c, the 10 kilometers of atmosphere is contracted by a factor of 16 down to about 600 meters. So even though the muon only lives 2 microseconds, and even though light only travels 600 meters in that time, that's enough because the atmosphere is only 600 meters thick from the muon's perspective. 2 different ways of looking at it, both correct, both giving the same answer. That's what I love about physics. When you really understand it, all the pieces fit together. So why does the universe freeze at the speed of light? Because that's the way space-time is structured. The speed of light is built into the geometry of the universe. It's the maximum speed of causality. It's the conversion factor between space and time. And because of the particular mathematical structure of space-time, with that minus sign in the metric, when you reach that speed, your time stops and your space collapses. It's not that there's something magical about 300,000 kilometers per second. It's that there's a fundamental speed limit built into the structure of reality. And light happens to travel at that speed because photons have no mass. If we lived in a different universe with different physics, the number might be different, but the principle would be the same. There would still be a maximum speed, and at that speed, time would still stop. You know, when I first learned about this as a student, it bothered me. It seemed impossible. How can time be different for different observers? How can everyone be right? But the more I thought about it, the more I realized that this is actually the only way it could be, given that the speed of light is the same for everyone. Once you accept that one experimental fact, that light always travels at c, no matter how fast you're moving, everything else follows by pure logic. Time dilation isn't mysterious. It's inevitable. And that's what I want you to take away from this. The universe isn't obligated to make sense according to our everyday intuition. Our intuition evolved to deal with things moving at human speeds, meters per second, maybe kilometers per second. We never evolved to deal with things moving at 300,000 kilometers per second. So of course it seems weird, but it's not weird. It's just different from what we're used to. The universe freezes at the speed of light because that's what the universe does. That's how space-time works. And once you accept that, once you really understand it, you start to see that it's actually quite beautiful. Time and space are not separate. They're aspects of the same thing. And the speed of light is the exchange rate between them. Every photon that enters your eye right now from the sun or from a distant star or from the light bulb above your head experienced no time during its journey. For that photon, its birth and death are simultaneous. The entire trip from its perspective is instantaneous. And yet from your perspective, it traveled for seconds or years or millennia. Both views are correct. Both are equally valid descriptions of reality. That's relativity. That's the nature of time. And that's why at the speed of light, the universe freezes. Not because time is an illusion, but because time is flexible. It's relative. It depends on how fast you're moving through space. And isn't that wonderful?